Hi guys, Mr. John here. Yes, in this video you will see another horrific switchmore power supply. Oh yeah, this time it rocks an integrated circuit. UC3842 to be exact, as you will see now. Here you can see the construction in all its glory. So, yeah, this circuit works, but it doesn't really work as I wanted it to. The frequency of operation is supposed to be 100 kHz. Transformer was calculated to be used at that frequency, but unfortunately with the components I use now, the frequency is more like 80 kHz according to the scope. So I will have to tweak it a little bit to get it closer. But it works as is. But what I wanted to say is that I managed to fudge it up. I did a major time screw up again. If that board layout on my drill controller wasn't enough. And I went, actually, this transformer has 3 windings, not including the one you see at the moment on the top. Primary, secondary and auxiliary winding, which is supposed to power the chip. And the thing is that that auxiliary winding is supposed to be 8 turns, but for some bizarre reason, when I was winding the transformer, I went to town and wound a little bit more, 18 turns to be exact. And that is pain in the ass. And that's, first I spent like 1 hour mucking around with this circuit. Thankfully I remembered that I used 18 turns in that auxiliary winding. I looked at the schematic and I just couldn't believe, like, why the heck will you have 18 turns on here if you have 5 here? The windings are coupled. So if I have 12 volts on 5 turns, how many volts am I gonna have on 18 turns? And the maximum supply for the chip is 30 volts. Then I went use some dropper resistors with existing 18 turn winding. It did work, but that kinda ruined. Here are these dropper resistors, by the way. Using dropper resistors there kinda ruins the whole point of that auxiliary winding, which is there to take to get rid of those power dissipation and to omit those resistors from the circuit. Use a high value resistor for so-called micro power startup, so you don't have to burn all the extra voltage across that resistor powering the chip, which requires like 30 volts or so maximum. So I went and I wound 8 turns winding, very sloppily, but it doesn't matter here. I'm gonna redo the transformer slightly anyway, because it's a complete disaster. So right now you can see 7 turns there, because when I measured the power supply voltage of the chip, which is, you will see right there on that meter, you will see that it will be pretty high. I do have an 10 watt bulb there, which is actually about 8 volts, so without further ado, let's plug it in, and I hope it won't explode on camera. And yeah, it hisses like crazy. 26 volts on the chip, which is fine enough value. You can see the bulb is glowing pretty nice and bright. That is because the output voltage is 12.7 volts, which is good. But the problem is that here you can see the rectifier. There is a diode down there, which I mounted on this aluminum heatsink using soldering. I soldered to aluminum. Piece of Englishman. Anyway, so. But this heatsink is not enough. The diode I soldered there is not a Schottky diode, it's just a regular PN junction diode, and it dissipates a hell of a lot of heat. This heatsink ain't gonna be enough for the load I plan to use it. I could have just omitted all this mess. I could have bought a ready-made supply which outputs 12 volts and handles 3 amps. That's what this is supposed to be. And that is for LED strip, which I bought, and I plan to probably, if not replace, just try to replace this fluorescence. I will just go and glue that strip right there on this white metal that you see there, and try how it will be. Will it beat fluorescence or will it be the same? Even if it's gonna be the same brightness, it's gonna be fine because it will consume less power. That if this power supply manages to hold it, because right now it does not. Not only the dissipation across on the secondary rectifier is too large, it doesn't handle 2 amps, it drops out. So maybe it is because of this mess. Yes, I'm using LEDs there as a voltage drop in the feedback to get the necessary voltage. This video I should really name it "How to Not Construct a Switch Mode Power Supply." Or I can be clever and call this video "How to Get Yourself Killed." And yeah, I'm fine with this stuff because I've been doing this for ages now. That's the way I started to assemble, if you can tell it that way. That's the way how I started to assemble my circuits. And I'm not dead yet. Anyway, so that's that. So I went and actually got rid of the optocoupler feedback. Now I'm relying on the perfect winding coupling, which in this case it's not, but even if it's not ideal, the thing still drops out, well, because the coupling between the auxiliary winding here, where the voltage is now sensed, and the secondary, which supplies your load, is very poor coupling. So the circuit now tries to keep the voltage the same on this winding, on the auxiliary winding, which powers the chip. But the advantage is now I don't have that horrific hiss. It works quiet. Absolutely nothing, just a little click when it kicks in. We have about 13 volts, which is fine. It floats a little bit, it still doesn't hold load, but the thing is that using this method you won't get perfect load regulation anyway. So you won't get perfect load regulation, which is meh. It's not critical for LED tape. As long as it is plus minus half a volt, I'm gonna be very happy. I'm gonna probably use a dimmer anyway. That will be secondary to it. I wanted kinda make the output voltage adjustable of this power supply, so I won't have to use anything else and will be able to adjust the brightness that way, but meh, whatever. I can always cobble a little PWM brightness control dimmer using 555 and a MOSFET. Not a big deal at all. So yeah, I'm very happy that it doesn't emit much noise anymore. So the waveforms must be looking better now. The diode still heats up quite a lot, and so does this ceramic capacitor, which is in the snubber network across the output rectifier. This diode on the heatsink, it still heats up quite a lot, because this kind of Soviet ceramic caps, I just don't like them at all. They just awful, to be short. Not only they die with time, and sometimes they go leaky, sometimes they go short, which is bizarre when you're talking about the ceramic capacitor, but they do go short sometimes. But the main problem with ceramic caps in general is they have a quite large dielectric loss. So if you push a lot of reactive power through it, it's gonna heat up. The actual dielectric will impose a loss there. So that's where the film caps excel. But film caps have a large equivalent series inductance, which is kinda which may not be all that critical as I think it is, but it's best to use a ceramic disc capacitor, not a multi-layer one. Multi-layer capacitors also has quite a large ESL, so that's why I used ceramic disc there. Anyway, let me give you one more demo. I do love that it's quiet. Anyway, I'm fine with that. We'll see. I started to lay out the board here, but we'll see. And another reason I ditched the optocoupler feedback is that it's kinda pesky. It will make layout look very bad. It is quite crusty already, and this is, by the way, is not to scale. This is just to give me general idea about the parts placement. Later I use a software with proper real-sized excuse me, footprints, so I'm gonna turn this into a PCB then. I might redo it, I don't know. We'll see. So I was curious, why that output rectifier heats up so much? I decided to scope across it and see what's going on there, and that's what I found. I found a lot of rubbish on it. See? Here you can barely see the square wave, and you can see a bunch of ringing, a lot of it. Bunch of ringing. Here on the top and bottom you can see the square wave. But if I'm gonna zoom in into that ringing, you see the sine wave, can't you? And the period of that sine wave is 1.6 microseconds. So I found a beautiful application note on the web which says me to measure that period of ringing, then find a capacitor experimentally which makes that period twice as long. I found it to be 47 nanofarads. Then I use this simple formula to calculate the value of a resistor necessary, 16 ohms. Here you can see that capacitor, which is that red disc capacitor, with a couple of resistors there near the scope probe. You know, if I'm gonna apply it, just push it onto the connection across the diode, it vanishes. And if I'm gonna zoom out, so you can see a bunch of shmoo, just press it in and shmoo disappears pretty much. There is still some rubbish, but without and with, big difference if you ask me. A lot cleaner. Now I'm gonna do some tests to see, will the diode run cooler? I don't know. The voltage across it does not exceed the normal ratings, but who knows?